Right, this session is solely on solving absolute value equations. This covers section 7.3 of your textbook. And we're just going to dive right in by working through some examples of solving these things. This is example 1 on page 382. And you're being asked to solve when does the absolute value of x minus 3 equal 7. Now, the trick in rearranging these is this absolute value, you're never really sure whether it's being applied or not if you've got a variable in there. For instance, if x is equal to 5, 5 minus 3 is 2, and the absolute value sign doesn't change anything. However, if x was equal to negative 7, negative 7 minus 3 is negative 10, and the absolute value does change things. So what you end up doing actually is solving two different equations in order to make this work. It helps a little bit in some cases to think of the graph of these things. So the absolute value of x minus 3, well, y equals x minus 3 itself would look something like this. So my 0 is here at x equals 3. This area would be unchanged by the absolute value sign. Whereas this region would be reflected by the absolute value. So if we wrote this as a piecewise function, we'd end up saying that the absolute value of x minus 3 would act just like x minus 3 for x values greater than or equal to 3, and would act like negative x plus 3 for x values less than 3. And that piecewise function is the basis for us solving this. If x is greater than or equal to 3, what I'm solving is x minus 3 equals 7, or x equals 10. If x is less than 3, what I'm solving is negative x plus 3 equals 7, or negative x equals 4, or x equals negative 4. Once you get your solutions, you do have to check to make sure they match your initial statement. Negative 4 is less than 3, so that's okay. And 10 is greater than 3, so that's okay. You can go forward and take a check. Negative 4 minus 3 is negative 7, the absolute value of which is 7. 10 minus 3 is 7, the absolute value of which is 7. Both solutions are valid, and x could equal negative 4 or 10, and be fine. I'm going to show one example of a word problem that comes along with these. The word problems are usually not too complicated, although the wording can make them a little bit weird. So let's look at example 2 on page 383. A computerized process controls the amount of batter used to produce cookies in a factory. If the computer program sets the ideal mass before baking at 55 grams, but allows a tolerance of plus or minus 2.5 grams, solve an absolute value equation for the maximum minimum mass of batter for cookies at this factory. So you're told that your ideal is 55 grams. You've got a tolerance plus or minus 2.5 grams. And it really seems kind of bulky and awkward and unnecessary to set up an equation to work out what the maximum and minimum are. 55 plus 2.5 is 57.5. 55 minus 2.5 is 52.5. However, we will set up an equation and solve it just to sort of go along with what we're asked to do in this case. So this is basically telling me that whatever my mass is, minus 55 grams, you're allowed to have a tolerance of up to 2.5 off of that. So if I were to graph out y equals m minus 55, I would know that for m values greater than or equal to 55, m minus 5, 55 equals 2.5, or m equals 57.5. For m values less than 55, negative m plus 55 equals 2.5. Negative m equals negative 52.5, or m equals 52.5. So my min and max values for m can be 52.5 and 57.5 grams. I only mention that because you will occasionally see a word problem set up sort of like this, and this is what you end up setting up and solving. And you can usually be fairly sure of what your answers are and whether they're correct for the setup. Okay, back into some more algebraic types of problems here. This is example 3 on page 384. And we're being asked to solve, when does the absolute value of 2x minus 5 equal 5 minus 3x? As before, your first step is going to write this as a piecewise function. So what does 2x minus 5 look like as a piecewise function? Well, we already know what the two parts are going to have to look like. It's going to be unchanged or reflected. So then our only question is, where's the boundary and how does this act around the boundary? So that's going to happen at my 0. 2x minus 5 equals 0 when x equals 5 halves, or 2.5. So then I just worry about above and below. If my x value is 3, this works out positive and my function's unchanged. So my function stays unchanged for x values greater than or equal to 5 halves, which means it's going to be reflected for x values less than 5 halves. Once I've got the piecewise statement, I can then make my solutions. For x being greater than or equal to 5 halves, I'm solving 2x minus 5 equals 5 minus 3x. If I subtract 5 from each side, I get negative 10 equals negative 5x, or x equals 2. We do have a problem here though. 2 is not greater than 5 halves. If you check that out in your original, 2 times 2 is 4, 4 minus 5 is negative 1, and the absolute value of negative 1 is 1, but 5 minus 3 times 2 is negative 1. My two sides don't add up. Since it's failed to meet that criteria, this is an extraneous solution. My other possibility for x less than 5 halves is that negative 2x plus 5 equals 5 minus 3x. Rearranging, I end up with x equals 0. 0 is less than 5 halves, so it meets that criteria. And if I check it here, 2 times 0 minus 5 is negative 5, the absolute value, which is 5. 5 minus 0 is 5. My two sides match up. My only solution is x equals 0. Now, it can be a little easy to overthink these sometimes. So let's take a look at this. Solve the absolute value of 3x minus 4 plus 12 equals 9. If I get that absolute value by itself, by subtracting 12 from each side, you get the absolute value of 3x minus 4 equals negative 3. Now you could go through the same process above, but what you're going to find out is that any solution you get is extraneous, because we cannot take the absolute value of something and have it come out to be a negative number. So this, quite simply, has no solution. If you get to some point where you have just an absolute value equals a negative number, there's nothing that makes that work. That has no solution. And now, just so people don't feel a little disappointed or let down by this, we go back to an old friend. which would be our quadratics. Hooray! Throw a quadratic into the mix, have a little fun with it. Now we still want to start the same way by writing out the quadratic as a piecewise function, but it will probably be a little bit more involved than our linear one. And it helps if we think of what a graph of this function is going to look like. So let's graph quickly y equals x squared minus 2x. Now this factors nicely into x times x minus 2, and this tells me my quadratic has zeros at 0 and at 2. The fact that it's a positive x squared means it opens upwards. And I can think about where my absolute value sign is going to make a difference and where it's not going to make a difference. For y values greater than 2 and less than 0, absolute value makes no difference. For y values between 0 and 2, the absolute value causes reflection. So my quadratic is unchanged when x is less than 0 or greater than 2. And it causes a reflection for x values between 0 and 2. And that leads me to my two things to solve. For x less than 0, or x greater than or equal to 2, I'm solving x squared minus 2x equals 1. Or x squared minus 2x minus 1 equals 0. I'm not sure if this is a nice solution or not. I think I have to go through the quadratic formula. Good times. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, or 2 plus or minus root 8 over 2, or simplified I'd have 1 plus or minus root 2. 1 plus root 2 is approximately 2.4, which satisfies my condition because it's greater than or equal to 2. 1 minus root 2 is approximately negative 0. There goes my brain. 1 minus 1, negative 0.4. That's terrible. I need to double check that. It might be negative 0.6. Oh, negative 0.4. Alright. Either way, it satisfies the condition that x has to be less than 0. So these are both okay. Now I also have to check out x values between 0 and 2. And in that case, I'm solving negative x squared plus 2x equals 1, or 0 equals x squared minus 2x plus 1. This factors quite nicely into x minus 1 times x minus 1. And so, just has the solution x equals 1, which is within my stated domain for that statement. So total solutions, x could equal 1 minus root 2, or 1 plus root 2, and those are all valid solutions to the original statement. One last example of solving these absolute value functions. This is example 6 from page 387. And we're asked to solve the absolute value of x minus 10 equals x squared minus 10x. So again, I will start by writing the absolute value expression as a piecewise expression. 10 is obviously going to be my boundary here. For x values bigger than 10, things remain unchanged. For x values less than 10, the absolute value sign causes a reflection. And I have two equations to solve. For x values greater than or equal to 10, x minus 10 equals x squared minus 10x. Bringing everything to one side, 0 equals x squared minus 11x minus 10, which factors nicely into, it does not factor nicely. Oh, that's a plus 10. It does factor nicely. Into x minus 10 times x minus 1. So my solutions are x equals 1 and 10. You'll notice that the 1 does not satisfy the condition, but the 10 does. So the 1 is extraneous. And for x less than 10, I'm solving negative x plus 10 equals x squared minus 10x. Rearranging, I end up with 0 equals x squared minus 9x minus 10. That also factors nicely into x minus 10 times x plus 1. And then x could equal negative 1 and 10. Negative 1 satisfies the condition, but 10 does not. Although you'll notice that it really wouldn't have mattered where I put the equal sign in my inequality. If I'd left it off over here, then both solutions would have been extraneous, but I would have got the 10 back over here. The negative 1 certainly meets the qualifier, so my solutions are negative 1 and 10. Both of which I could check back in the original. Negative 1 minus 10 is negative 11, the absolute value of which is 11. Negative 1 squared is 1, minus 10 times negative 1 is also 11. 11 equals 11, and it works out. 10 would give me a 0 on each side, which also works. Okay, so those were a few examples of solving absolute value equations. There'll be some associated questions in the Google Classroom with that as well. All we really have left to talk about now are reciprocal functions, which we'll talk about next session. All right, everybody. Thanks for watching.